Hello, everyone. My name is Yaotian from the Chinese University of Hong Kong, China. So I present paper, Decentralized Epoch-based F2FS journaling with fine-grained crash recovery. So here is my outline. First, I will give some backgrounds and then introduce the motivation of this paper. And next, I will give some design challenges and the details, and finally give the evaluation results. So for the backgrounds, as you can see, F2FS is widely used in the Android smartphone manufacturers. And despite we have the battery power in our smartphones, crash recovery, the crash is everywhere. For example, the low temperature can shut down the Android phones, and also the outdated applications and system upgrades can cause the phone to reboot. So the crash recovery is very vital. And for the F2FS overview, firstly, it matches the storage device with the segment, and the segment is 2 megabytes per segment. And for the on-disk stage, firstly, it has the in-place update errors. So the first one is the checkpoint error, which is used for the crash recovery by rollback the file system to a consistent stage. And then it also stores some file system metadata in this in a random write error, like the segment information table, the SIT, which is used for the space allocation, and then the node address table, the NAT, which is the mapping table for the I node and the D node. And next is the segment summary error, SSA, which stores the reverse mapping for the garbage collection during the migration. And also it has the auto-paste update error, the local structure way. So it stores the file metadata like the I node and D node in this error, and also the file data in this error on the data segment. So for the F2FS checkpointing, it is used to roll back the file system to a consistent state by the most recent checkpoint pack. And however, the checkpointing can severely degrade the system performance because once the checkpointing triggered, it will write back all the dirty in-memory data and metadata to disk, and all the file read and write activities will be blocked until the checkpointing is complete. Here I also summarize some issues of the F2FS checkpointing. The first is there's the time overheat. For example, checkpointing can lead to long-tail latency. The 19% latency can larger than 240 milliseconds during the checkpointing in our experiment. And the second problem is that it can induce more data and metadata loss. This is because if the data and metadata are not checkpointed, it cannot be recovered yet. And so the F2FS checkpointing can only provide the coarse-grained crash recovery. And the third problem is that the inconsistent roll-forward recovery. Briefly speaking, F2FS F-Think provide 3 F-Think modes to persist the data and metadata. However, for the no barrier and the POSIX mode, due to the I/O reordering, the metadata can be persistent, but the data is not, so it will lead to some inconsistent issue. So to address the coarse-grained crash recovery, we propose to use the journaling for the F2FS. Then we want to figure out why existing journaling mechanisms cannot be used to F2FS directly. So we get into our motivation part. In our paper, we only discuss about the order journaling, which will flush the data before commit the journals and only journal the metadata. As an example, with ext4, which is also a widely used journaling file system. So as you can see, firstly, we have the new data in the memory. And then we have the new inode corresponds to this new data, like the new file size. And due to the fixed location of the inode, there is no need to modify the file system metadata like the bitmap. So to persist the new data and the new inode, we first need to flush the data to the disk. And then we flush the new inode to disk. Yeah. And the results, if we adopt the order journaling for ext4, we only need to journal the new inode. And then if a crash happens, we can apply the inode journal to the original location for crash recovery. Yeah. And however, if we adopt the order journaling mode for F2FS, which is auto-paste update file system. We need to journal both the file system metadata and file metadata. And similarly, we have this example. New data is in the memory first, and then a new inode corresponds to this new data. And the next, due to the auto-paste update characteristics, we have the new file system metadata in the memory. So here we can see the new SIT entry, NT entry, and SSA entry. So to persist the file system, we need to firstly flush the data to the new location, and then persist the new inode to a new location. And finally, we write back the file system metadata to their final location. So if we adopt the order journal mode for F2FS, obviously we need to journal both the file system metadata and file metadata. And well, there are more I/O overheads and journal overheads will be induced. And if we only journal the inode like the ext4 does, we cannot do the correct recovery because after we recover the new inode with the inode journal, the outdated file system metadata still points to the old inode. So next, in the design part, I will introduce the issues of utilizing journaling for F2FS that needed to be addressed and our design details. The first issue is the big overhead with page-based journaling. So which means that the conventional journaling mechanism like GPT-2 journal the metadata and the page granularity, so it will induce storage overhead and journal apply time overhead, which means that it will require more on-disk journal space, and the journal apply will be triggered frequently to reclaim the journal space. So in our experiments, you can see the GPT-2 apply time can occupy a big portion of the total journaling time. And for our solution, we only journal the metadata changes, and we will embed the metadata changes as logging into the per inode log list. So the metadata changes will from the inode as the file system metadata changes, and also the file system metadata changes from the SIT, NT, and SA. And in this way, we can require less log space, and the journal apply will not be triggered frequently. And for the second issue, the locking overheads due to the centralized journal design for the existing mechanism. Also the GPT-2, so it will lock on a global journal ticket. So for the journal ticket, which means that for each file operation, it needs to require a journal ticket. And this value of a ticket tracks the number of the ongoing file operations that has not been finished journaling. So there are some lock contentions on this journal ticket, and also it uses centralized log list and the log contention on this global log list. Also, with our experiment, we can see the locking time occupy a big portion of total journaling time. And for our design, we use the decentralized per inode log list. So as you can see, inside each inode, they have several log lists, and each log list corresponds to different journal periods. Yes, so one inode log list is used to record the related logging. And in this way, we can significantly reduce the log contention and interference among the inodes, because for one file's log, you can insert your log into your own inode log list. And the third issue is the non-waiting times during journal period transfer. So in the GPT-2, the new transaction for the next journal period cannot be directly issued because it's coupled the control plane and the data plane. Specifically, the preceding transaction need to wait the file operations that has not been finished the journaling. So in our experiments, we can see the waiting time of the journal period transfer also occupies some portion of total journaling time. And for our solution, we decouple the data and the control plane with Epoch. So as you can see, each journal period corresponds to one epoch. And for the data plane, we embed the metadata changes as logging into inode log list. And for the control plane, we only register the inode information to the epoch. So in this way, when we transfer to next journal period, there is no need to wait the ongoing file operations on the data plane. Yeah. And to reduce the journal applies overheads by writing small logs one by one, we choose to write back the in-memory metadata pages. So to achieve this, we have 3 page state specifically. If the page state is up to date, which means that the page has the same counterparts as is on disk, yeah. And if the page state is F2FS dirty, which means that the metadata page has been modified and the changes has been recorded but not committed, and the data has not been flashed to disk. And if the page state is dirty, which means that the changes has been committed but not applied and the data has been flashed. So the dirty page can be used for journal apply. So with these 3 page states, we have fast forward to latest journal apply. As you can see, if the page state is dirty, we can directly flash the dirty page and set this page state to up to date. And if the page state is up to date, we can skip this record. And if the page state is F2FS dirty, we can apply the unticked journal record. So with this example, we first read the Epoch-1's journal record to memory and locate the in-memory inode 1's page by the inode number. Then we see that the page state is dirty, so we apply the inode 1 to disk, and then we update the file system metadata and write the file system metadata to disk. And next, we read the Epoch-2's journal record and also locate the in-memory inode 1's page by the inode number. And then time we can see the page state is up to date, so we can skip to apply the inode 1's page. Yeah. And for the crash recovery, it will be performed by reading the journal records from the journal file and apply the journals in order. So we will locate and read the older inode to memory and apply the metadata changes with logs, yeah, and also update the file system metadata. So here, after the crash, for the crash recovery, we read the Epoch-1's journal record to memory, and then we will read the old inode to memory. And then next, we apply the log in the Epoch-1, and then we jump to the Epoch-2's journal record. So we apply the log in the Epoch-2, and finally, we apply the recovery the inode 1, and then update the file system metadata. So the next part is our evaluation. We have implemented the F2FS by defining the various log types and also modify some data structure to implement the per ILO log list and the sum mapping tables, and also have 2 kernel threads for the general commit and apply. And for the log area, we in our implementation, it requires 256 megabytes. And for the environment, you can see some test-based information. For the benchmarks, we have we use the file bench like the metadata intensive workloads, small file intensive workloads, and data intensive workloads, and also have some mobile bench for the Android workloads. Yeah, so for the evaluation, we mainly compare the F2FS with F2FS checkpointing. So as you can see in the first figure, F2FS can significantly reduce the checkpointing time by up to 5 times. And for the non-tail latency, we can see with the CDF of latency figures, it can eliminate the checkpointing non-latency. And for the overall average file operation latency, it can reduce the average latency by up to 35%. And to conclude this paper, F2FS provides the fine-grained crash recovery by journaling and also eliminates the non-tail latency of checkpointing. And to reduce the I/O and storage overheads, it only journal metadata changes, and also have some novel designs like decentralized journal design with per idle log list to minimize log contention and decouple the data and control plane to eliminate the non-waiting times during journal period transfer, and also use the fast forward to late journal apply to consolidate the multiple small writes. Yeah. And also the source code has been released for the access. So thank you. That's the main idea for this paper. Any question or comment?